Alright guys, gals, let's continue our discussion on the chemistry of life. And I know, yes, I'm squeezing a lot of material into a really short period of time, but this is the obligatory chemistry review chapter. So we left off on chemical bonds. Let's talk about a chemical bond. And for our purposes, a chemical bond is really something that holds an atom together with another atom within a molecule. So it's one atom being held together with another atom. Multiple atoms being held together make a molecule. And there are several kinds of chemical bonds. The kinds that we're going to talk about are the classics that you get in your high school chemistry class. So we're going to first talk about ionic bonds. An ionic bond is, simply put, an attraction between an anion and a cation. So we talked about how there can be ions and electrolytes. If you have these substances in a solid state, they're going to be called crystals, and they're held together with ionic bonds. To form an ionic bond, we need to make an ion. To make that ion, we need to donate electrons from one atom to another atom. A key characteristic of the ionic bonds is that they're easily broken by water. Then we have covalent bonding. Covalent bonding really is the permanent bond. It's the strong bond. This is the bond that's not broken by water. I should back up a little bit here. Because ionic bonds are easily broken in water from a human perspective, and really that's what we care about this class, is the human perspective. From a human perspective, we don't really care that much about ionic bonds because they're constantly broken inside of the human body. We are mostly water. Most ionic bonds aren't going to survive being present inside of the aqueous human being. Let's go back to covalent bonds. There are two kinds of covalent bonds. Both of these are super strong. When we think of covalent bonds, I want you to think of sharing electrons as opposed to transferring electrons with the ionic bond. And the sharing of electrons between atoms makes it so that the atoms, excuse me, early morning here, makes it so that the atoms have a very strong attraction between them. Now those electrons are going to be equally shared. So if we have equally shared electrons, we call that a nonpolar covalent bond. And here's an example of a nonpolar covalent bond between two hydrogen atoms making a hydrogen molecule. It is going to be perfectly in between the two nuclei of those hydrogen atoms. We could also have a polar covalent bond. And when we think of a polar covalent bond, guys, girls, I want you to think of sharing but unequal sharing. Kind of like my 4-year-old when he's sharing with my 2-year-old. He's technically sharing, but it's definitely not equal sharing when they share between the two of them. And if we have this unequal sharing of electrons, this is going to make it so that there's some unique characteristics. One of those unique characteristics is that there's a partial charge. And on this diagram right here, we can see that there's a partial positive, a delta plus, and by the oxygen we have a delta minus. And those partial positives and partial negatives of the uneven or polar covalent bond makes it so that we can have a new thing formed. This new thing is an intermolecular bond, a bond between molecules. We can have a hydrogen bond form. And that hydrogen bond is going to form between a partially negative oxygen and a partially positive hydrogen. So partial negative oxygen, partial positive hydrogen, and that dotted line in between them, I know it's really hard to see my mouse cursor right now, represents the hydrogen bond. Hydrogen bonds hold molecules together temporarily. So water molecules, they're the classic example of hydrogen bonding. And when we think of water molecules, there's a lot of fluid tension or surface tension. These molecules tend to stick together. Anyone who's ever tried to belly flop off the diving board into a swimming pool can attest that water molecules kind of stick together, and it kind of hurts when you belly flop off the diving board into a swimming pool. Other molecules in our body have lots and lots of hydrogen bonds. For example, DNA molecules and protein molecules have millions or thousands, depending on the size of the molecule, thousands to millions of hydrogen bonds holding them together and giving them the unique shape that they have. So let's make sure that we can define some terms. I alluded to these, but let's make sure we're crystal clear. A molecule is any chemical that has two or more atoms, and those two or more atoms are going to be held together by a chemical bond. When we have a chemical compound, that's going to be anything that's made of 2 or more elements. And those 2 or more elements need to have a chemical bond holding them together. It can be an ionic bond or a covalent bond. So molecules are 2 atoms, 2 or more atoms held together by specifically a covalent bond. Compounds are going to be 2 or more elements bound together with any kind of a bond. So hydrogen bond, ionic bond or covalent bond. And then finally with molecular formula. For a molecular formula, this is going to be for molecules held together by covalent bonds. And molecular formulas tell you exactly how many atoms of each element are present. So here we have a 6 and a C for carbon. So we have 6 carbons. Here we have 12 hydrogens and 6 oxygens. C6H12O6 for the molecular formula, just as an example molecular formula. Now, when we look at water, water is a key component of our body. Our body is mostly water by weight. And we use this water to make a lot of mixtures in our bodies. These mixtures are defined by the fact that they're physically blended together, but not chemically combined. So when we make a mixture in our body, we are going to be, I was going to say mixing. I don't want to use the word mixing in my definition of mixture. When we make a mixture in our body, we are going to take molecules or compounds, and we are going to randomly interdisperse them with each other. But the thing that we do not do when we make a mixture is that we don't form chemical bonds. We don't make or break chemical bonds by making a mixture. So they are not chemically combined. And because they are not chemically combined, mixtures can be relatively easily separated from each other. Now, with that said, in our body, we are very complicated mixtures. There are dozens upon dozens of different chemical compounds dissolved in the aqueous solutions of our bodies to make up our mixtures. If you look at the human being, we're 50% water weight to 75% water weight, depending on some variables like age, sex, fat content, etc. Generally speaking, babies, infants have more water, and geriatric patients have less water. Generally speaking, females have more water, males have less water. Generally speaking, individuals that have lots of adipose tissue have more water, and individuals with less adipose tissue have less water in their bodies. As we're making these solutions and these mixtures with water, we need to really emphasize some of the cool properties of water, particularly that water is able to dissolve a wide variety of chemical compounds. We call it the universal solvent. Some molecules, though, are really easily dissolved in water. And those that are really easily dissolved in water, or that dissolve in water in general, are called hydrophilic. Hydro is a root word for water. Philic is a root word for, well, brotherly love, if we wanted to really look at the Greek word. But in this case, in a scientific setting, we're going to think of love. So, water-loving. A water-loving molecule easily dissolves in water. The old rhyme my chemistry prof taught me was that like dissolves like. So in this context, if we have a polarized molecule or a charged molecule, it can dissolve really easily in water, which is a polar covalent chemical compound. We also have hydrophobic, water-fearing. Think of phobias or phobic. Phobic means to fear. Water-fearing, I think I just said water-loving. I meant to say water-fearing. Water-fearing substances, or hydrophobic substances, don't dissolve in water easily. So when we think of these hydrophobic substances, guys, gals, these are molecules, chemically speaking, that are neutral. They don't have polar covalent bonds. Instead, they are going to have non-polar covalent bonds. And they have a hard time dissolving in water. The classic example in a human being is going to be fat or adipose, or any kind of a lipid. For our metabolic reactions, so all the chemical reactions we need to stay alive, these reactions depend on our ability to dissolve things in water. As water starts to dissolve something, it's going to form hydration spheres. And these hydration spheres overpower the ionic bond. So here's a sodium, here's a chlorine from a sodium chloride. All of the negative oxygens here in this water are going to be directed towards the positive sodium ion. And if we look at this chloride over here, on the right side of the screen, all of the positive hydrogens in these water molecules are going to be directed towards the negative chloride ion. So this is what happens when we take ionic chemical compounds and put them into aqueous solution or into a water-based solution. Water will form a hydration sphere around the ions and overpower the ionic bond. As we make solutions in our body, it's important to define some key terms. Solutions are going to make two things combined. We have a solute and a solvent. Solutes plus solvent make a solution. The solute is whatever we have less of, generally speaking. In most situations, solutes are going to be solids, and the solvent is going to be water, because water is the universal solvent in human beings. So whatever we have more of, in almost every case, is going to be the solvent, and then the solute is whatever we have less of. And then combining them together, mixing them together, gives us the solution. Our solutes can be gases, solids, or liquids. Most solutes in the human being are solids that have been dissolved within the water or within the aqueous solution. And as we look at this aqueous solution, one of the solutes that we can have in the aqueous solution is a hydrogen ion. And this hydrogen ion is very significant because as we change the concentrations of these hydrogen ions, we can go from an acid to a base. Acids are going to be any chemical compound that donate hydrogen ions or donate protons to solution, and bases are going to accept protons or accept hydrogen ions. Another way to think of a base is that it's something that releases hydroxide ions, OH minus ions, to solutions. And as we add acids or add bases, we change the concentration of protons or hydrogen ions in solution, and we change the pH of solution. And as we're looking at pH, pure water is going to have a pH of 7.0. Or it's going to have a neutral pH. And at that neutral pH, the number of hydrogen ions is going to equal the number of hydroxide ions. If we have more hydrogen ions than hydroxide ions, the pH will be acidic. It's less than 7 and acidic. And I need to emphasize that less than 7 is acidic, we have more hydrogen ions. Greater than 7 is basic, we have hydroxide ions. So if we look at a pH scale here, pure water is right in the middle of the pH scale. Egg whites, they're slightly basic at the pH of 8. But notice, guys, gals, most of these things that are listed over here, these are food products. And most of these food products are acidic. We as human beings have a lot of adaptations to handle acids in our body. If we look at our stomach over here, our stomach is more acidic than all of these food products that we eat, with the exception of egg whites. And then if we look over here, cleaning chemical compounds are, generally speaking, going to be basic in nature. A good rule of thumb is that if you eat it and it tastes tart, it's going to be acidic. Or if you can feel it and it's slippery to the touch, it's probably a base. Let's talk about energy and work. In our bodies, guys, gals, we have energy. We store energy and we use energy. And we define energy as the ability to do work. To do work means that we move something. What do we move in our bodies? We are going to move chemical compounds from point A to point B in order to maintain the concentration gradients that we need to stay alive. Every form of activity in our body is some kind of a work. All activity is a form of work in our bodies. And there's two kinds of energy that are the most common in our bodies. Kinetic energy, the energy of movement or the energy of motion, and then potential energy. Potential energy you can think of as stored energy. And in our bodies, the energy of motion, generally speaking, is going to be from us physically moving our bodies, from contracting our muscles. And then here we have potential energy. And the most common potential energy in our bodies is going to be the chemical energy of the food that we eat, the energy inside of the chemical bonds that hold the molecules in our bodies together, that hold the molecules of the food that we eat together. We can take the energy from the food, from the chemical bonds of our food, and use that energy, transform it, and store it in our bodies as an altered form of chemical energy in slightly different chemical bonds to be used at a later time. As we have these chemical reactions in our bodies, we can use these chemical reactions, this energy in our bodies to form chemical reactions. So we can use the energy in our bodies to power chemical reactions. And when we are powering these chemical reactions, there are things we can do that influence the rate of chemical reaction. When we have a chemical reaction, we are making or breaking a chemical bond. Making or breaking a bond is a chemical reaction. And when these reactions occur, physically speaking, you can imagine molecule A is going to have to physically smash into molecule B in three-dimensional space. They have to hit each other. And for them to hit each other, they need to hit each other at the right orientation, at the right speed. You know, there's a lot of statistics involved with this. We can cook the books, so to speak, and make this more likely to happen if the reactants we are using, those chemicals we are using, are more concentrated, if the temperature increases, or if we have a catalyst present. Now, when we think of a catalyst is anything that is going to speed up a chemical reaction. Catalysts speed up those chemical reactions by lowering the rate of reaction. Or lowering the activation energy for that chemical reaction. As we look at catalysts in our bodies, most catalysts are made of proteins, and we call them enzymes within our bodies. They speed up or facilitate those chemical reactions. Catalysts in our bodies, as they're being facilitators of our chemical reactions, these catalysts don't actually get used up in the chemical reaction. That can be used over and over and over again. So a small concentration or a small amount of catalyst can make a very dramatic difference in the overall rate of reaction. And this is a good stopping point for us. We are going to have one more lecture recording on chemistry of life where we focus on carbs, lipids, proteins, and nucleic acids. But at this point, we are nearly done with our crash course on chemistry. Happy studies. If you have any questions, please shoot me an email or send them or swing by my office hours. Have a good one.